Well, good evening, everyone. My name is Tim Hitchens. I'm the president of Wolfson College, and it's a great pleasure to welcome John Ioannidis to give this year's Haldane Lecture, named, as many of you will know, after the remarkable father and son scientists who lived and worked here by the Chalmers River in Oxford, where Wolfson College now sits. If you're interested in their story, do please watch the interview I did earlier this year with Samantha Subramanian about JBS Haldane on the college's YouTube channel. Well, John needs little introduction. He's speaking to us from Stanford, morning John, where he is Professor of Medicine, Health Research and Policy, and Biomedical Data Science. He's an expert in evidence-based medicine, epidemiology, and clinical research, though I think it's fair to say he's also an expert in modesty. In his Stanford bio, he says he does not run his own social media account since, he says, I make a lot of errors. I need to revisit my writings multiple times before publishing, and I see no reason to make a fool of myself more frequently than is sadly unavoidable. He spent a lot of time researching research and draws attention to its flaws. Wikipedia, always a very reliable data source, reports that his paper in 2005 on why most published research findings are false is the most accessed article in the history of the Public Library of Science, at least until 2020. A very brief canter through his CV. He was born in New York City, raised in Athens, Greece. He was top rank in his medical school class at the National University of Athens. He also received DSc in biopathology from the same institution. Trained at Harvard and Tufts in internal medicine and infectious diseases, then held positions at NIH, Johns Hopkins, and Tufts. He chaired the Department of Hygiene and Epidemiology at the University of Ioannidis Medical School between 1999 and 2010, and then moved to Stanford. John has kindly agreed to take questions after his lecture, so please do use the chat function in YouTube if you have questions, either then or throughout the lecture. So we're honored to welcome John with us this evening, and he will speak to us on meta-research in quest of reproducible and useful evidence. So John, the floor is yours.
Thank you, Tim. Thank you for the very kind invitation and the great honor. It's a great honor for me to deliver this annual Haldane Lecture. And I love Oxford. I wish I could be there in person. I hope that it will happen some other time soon, when hopefully this tragedy will be over and our world becomes more normal again. So let me share my screen. What is meta-research? It sounds like a fancy term. It's a discipline that is trying to evaluate and improve research methods and practices. And in that sense, it's almost synonymous with science, because science is about using research methods and practices, but it has probably the added component that it focuses on how exactly can we optimize our use of the scientific method. So how can we optimize the way that we perform research, the way also that we communicate research, and this has become clearly a major challenge in the last year and a half. How do we verify research? How do we evaluate our research products? And how do we reward research and investigation in a way that our incentives are aligned with getting the most reliable science possible? This is a map of recent science that I have been working on with my colleagues in SciTech, Kevin Boyack leading the team. And it shows all the disciplines of science. There's the big disciplines like medicine and physics with a separate color. And then there's close to 500,000 subdisciplines that each one of us is struggling to come up with something interesting. This is a universe that here has only about 20 million dots of papers, but actually the full universe is close to 200 million published items. And I have an arrow here that this is my best paper, or so I think. It is a speck of dust in a speck of dust in a speck of dust, somewhere around that part of the universe. Some preemptive comments. This universe is amazing, and science is the best thing that can happen to humans. The research needs to be supported with heightened commitments. We have realized that in times of crisis, even more so. Most research, however, done to date has been non-transparent. Much of it has been non-reproducible. It's not really easy to put trust to what is being published. We mostly put trust without being able to really see the evidence, which is a major departure from the original initiation of the scientific method and the Royal Society, nullius in verba. I would not trust anything just because you're telling me. I need to see the data. I need to see how it works. I need to be able to get the same result as you have obtained. This is some mapping that we did with machine learning approaches and algorithms where we text mine the entire open access PubMed Central over 30 years. We published that work in PLOS Biology recently. And this is in different countries, the publications that are sharing their data. And you see lots of dark color. There's no country really that has a sizable proportion of their data of papers published in the last 30 years that are being shared. How about a registered protocol, which is one way to enhance trust because one can see that there was a protocol ahead of time and one can compare what was in the protocol compared to what was done. Again, you see that the globe is in mostly dark colors for these last 30 years. Not only transparency is questioned, but also utility. And I would argue that a large proportion of research does not need to be useful. It can be just blue sky science with open-ended questions that you iteratively try to realign. But when it comes to clinical research, for example, we need to make sure that research is eventually useful. So what are the different types of utility or the different features of utility that we may want to have? These are 8 features of utility that I have cataloged that I think are important to think about. Problem-based. We need to do applied research that is tackling some problem that is big and important enough to fix. Context placement. We need to know what else has been done before and systematically assess our prior knowledge to inform the need for any new studies. Information gain. If we know what has been done in the past and we have some plan on what to do now with a new study, is that study large enough? Is it definitive enough? Is it long enough to be sufficiently informative, regardless of what the results are? If we have information gain potential only if we get a particular type of result, then people will try to get that result, and this may only lead to further bias. Pragmatism. Are we dealing with research that reflects real life? And if it deviates, does it matter? Patient-centeredness. Does the research reflect top patient priorities? Have we asked people what do they care about and what matters to them? Value for money. Is the research worth the money? We have lots of competing ideas and lots of competing protocols and lots of potential divergent directions that we can take our research. So have we decided in a thorough way that this new research investment is worth it, especially compared to others? Feasibility. Can we do it? Very often I have very ambitious plans for the research that I want to do, and very quickly I realize that, well, I don't have the resources, I don't have the skills, I don't have the capacity to do it. I'm grateful when I realize that pretty quickly, but sometimes I spend weeks and months and years and then nothing can be done. And finally, transparency, where it comes back to the issue of trust. And this is the point where utility and reproducibility come together. The methods, the data, and the analysis need to be verifiable and hopefully as unbiased as possible. Probably it's never possible to have the totally unbiased study, but we have thought about biases and we have tried to minimize their impact. If you look across the board of all medical research, only very few studies of those that you will see published in peer-reviewed journals meet these criteria, or even, let's say, 5 or 6 or more of them. Even if you decide to just read the top highest impact factor journals like New England Journal of Medicine, JAMA, Lancet, BMJ, they would still fail in the majority of studies and in the majority of the criteria that I just mentioned. In contrast to utility and usefulness, significance is something that almost all papers that you will see published claim. And the easy way to claim significance is statistical significance, but even if there's no statistics, very often you will see the term significant being used regardless. This is an empirical evaluation looking at the papers that did use p-values and statistical significance testing across the biomedical literature from 1990 to 2015, and 96% of these papers claim statistically significant results in their abstract, if they had p-values in their abstract, or in the full paper, if they had p-values in the full paper. I would argue that this means that statistical significance is becoming a boring nuisance. Every study is statistically significant, so this is no longer a very good discriminating feature that can tell us which one should I believe and which one should I consider useful, even less so. We have lots of empirical studies that suggest that in some fields and some designs of medicine and also other fields, the studies always get the right results. This is one example. We looked at all the trials that had a sufficient sample size and published in a single year using non-inferiority designs with head-to-head comparisons and sponsored by the industry. 96.5% of them had results that were favorable to the sponsor. They said that the sponsor drug is non-inferior, and therefore this is a good result for that specific product. I would argue again, if we have a tool that 96, 97% of the time gives you the same answer no matter what, its ability to discriminate what is really true and what is really useful is very, very diminished. We've seen diminished effects in many types of studies where initial published results are very spectacular. They suggest that we have found something that is a major discovery. But then when we run better, larger studies, we see that the effect sizes are smaller. For example, this is an empirical evaluation looking at the most highly cited studies of biomarkers in the biomedical literature, comparing the results in terms of a relative risk of an effect size in the highly cited study against the relative risk in the largest study. And you see that almost all the points are below the diagonal, which means that the largest study almost always finds more conservative, less spectacular results compared to the highly cited study. So the quest for reproducibility has led to a lot of debate and also to a lot of confusion, because there's a lot of different terminology that is used interchangeably, and some of that is interchangeable, but not necessarily. So terms that are very popular include reproducibility, replication, and then you have different types of replication: exact replication, conceptual replication, reanalysis, repeatability, corroboration, triangulation. And people use these terms in different ways across different fields. All scientific fields are using reproducibility or related terms more frequently, and this is an empirical evaluation of all 20 major scientific fields. The use of these terms is becoming more and more common over time, but they mean different things because they also have different aspects of the scientific method that they endorse more than others, or that they think is more important compared to some other features. So differences across scientific fields relate to the degree of determinism, the signal to measurement error ratio, the complexity of designs and measurement tools, the closeness of fit between the hypothesis and the experimental design and data, the statistical analytic methods to test hypotheses, the typical heterogeneity of experimental results, whether there is a culture of replication, transparency, and accumulating knowledge in the field, or replication is considered as me too, kind of second-class research, what kind of statistical criteria are used to claim truth or make any claims, and finally, whether the field is theoretical or applied and has some specific purposes to which the findings will be put. And also that means that there may be consequences of false conclusions. If it's applied research in medicine, that could mean lots of people dying if we make the wrong decisions, if we use the wrong evidence, if we use research that is suboptimal. We can probably put reproducibility into three major bins, regardless of the differences across fields. Reproducibility of methods pertains to the ability to understand what exactly has been done in a scientific investigation. Being able to read the methods section, which is typically in small print, it's erratic, elliptical, and esoteric, or all of that in many cases. So if we can read the methods and then go to the lab or go to the clinic or go to our laptop and make them work again, this is good news. It means that these methods are alive. We have sufficient detail to be able to repeat exactly as possible the experimental and computational procedures. Reproducibility of results pertains to a different type of replication per se, where we have new studies, not the existing study, but we design a new study and we can make it as faithful to the original one, or we could try to deviate in some aspects for whatever reason. But basically, we try to follow the same methods, the same experiment sequence, and try to see if we can produce corroborating results. And finally, reproducibility of inferences is what happens at the end of not just one study, but it could be 2 studies, it could be multiple studies, it could be an entire field, and you call the experts to read the literature and try to make knowledge claims from these study results. And they may agree, but also they may disagree. Sometimes they may vehemently disagree in what they conclude based on the same data that they all see, and hopefully they see them in a transparent manner. This is a stereotype exercise of what could go wrong in a typical situation where we are running studies with limited resources and therefore with small data sets. This is probably the most common stereotype that is very prevalent across scientific fields, both in medicine and in other scientific disciplines. We have lots of very smart people competing for limited resources. This means that most of us can run small sample size studies. We have to compete against each other. We need to prove ourselves as principal investigators who are better and more competitive compared to others. Each one of us typically has a small team. Our work tends to be siloed in that competition. We need to convince funding agencies that we have found something interesting. So we need to search very hard in our data and often cherry pick results that look the nicest of all. A lot of that is done post hoc in an exploratory manner. Statistical methods that are used are very lenient, so a p-value of less than 0.05 is enough. There's no registration, no data sharing, and no replication, because none of that is really going to help, at least in an environment where you need to say that I have found something. If you replicate, you have a very high chance of eventually realizing that you haven't found anything, or data sharing is offering ammunition to competitors, and registration is limiting the degrees of freedom that one would have to explore different possibilities and perform different analysis. So it's a malignant stereotype, and I'm not saying that I have any specific scientist in mind or any specific scientific field, but I think that we see a lot of that stereotype occurring, and empirical evaluations have happened in many different scientific fields that show the dominance of these small studies. This is one such that we published recently with Dennis Sukes, looking at the sample size evolution in neuroimaging research. We looked at highly cited studies over 22 years and also recent practices. You see some improvement on the median sample size of studies that goes up from about 5 in the early 1990s to something like 22 or 25 in recent years. All of these are very small studies. They're looking at very complex questions with very limited sample size possibilities. This is not just in neuroimaging. A few years ago, we looked at very different fields across neuroscience, ranging from basic science to applied and clinical research. And we saw that the common denominator was that most of them were using very small sample sizes with unavoidably very low power to detect positive associations, but also very high risk of false positives, even with a tiny amount of bias if they detected some signal. It's not just in medicine and biology and life sciences. This is data from economics, where we looked at more than 10,000 studies with Christo Kouliagos and Tom Stanley, looking at the power of these effect estimates, more than 70,000 effect estimates in 130 fields of economics. The vast majority of these studies were vastly underpowered. There's another stereotype that I want to discuss, which is becoming more common. In some fields, it is becoming actually substantially common, but it's still probably a minority. It's the stereotype of big data, which have become very prominent in some areas that use high throughput biology or electronic health records. Here we have the opposite issue. We have extremely large sample size studies that are overpowered. They are likely to detect statistically significant results, especially with lenient thresholds. It will happen all the time. Lots of cherry picking does happen there because it's mostly exploratory, again, mostly post hoc. Idiosyncratic statistical inference tools might be used, far more sophisticated, but without much consensus. No registration is the norm. And data sharing does happen, but with very complicated ontologies that do not match across different fields, and with very poor description sometimes of what exactly is being shared. So if people use data from other investigators that they're not aware of what exactly these data stand for, we run into extra trouble in rerunning these analyses. So big data are offering a huge opportunity, but at the same time, they can lead to even bigger noise and even bigger error. Many fields have realized that they need to change these norms, and many fields have gone into soul-searching mode in the last decade, and we've seen some efforts of reproducible science and reproducibility checks. For example, psychology, this is a classic paper published in Science in 2015. Leading psychologists from 271 institutions joined forces. They decided to try to reproduce experiments that had been published in their top impact factor journals, some of the creme de la creme journals of the field. And as you realize, most of these creme de la creme papers could not really be reproduced. It depends on how exactly you define reproducibility, based on p-values, based on effect sizes, on overlapping confidence intervals, but you can see clearly that the results were different very often. Another reproducibility check, looking at papers that were published in Nature and Science, not really much better. A lot of studies could not be reproduced at all. The effect sizes in the reproducibility effort were practically null. And in many others, they could be reproduced, but the effect sizes were substantially smaller compared to the original publication. Can we predict which studies will not be reproduced? Maybe to some extent, if it's a field that has some knowledge circulating in the field, we can do a little bit better than chance, but we are very far from being able to predict exactly which study will not make it and which study will be successful upon a reproducibility check. And I would argue that in fields that have very little knowledge that might be circulating, or most of the knowledge is agnostic, it may be almost impossible to make any educated claim. In some fields, it has been worse than others, but also some fields have made greatest improvements compared to others. For example, genetic epidemiology used to be completely irreproducible. Based on what we know now, for many years, all the candidate gene studies that we were publishing, their validity was probably in the range of 1%, at least based on what we knew. When we moved to a new paradigm of research that was more transparent, large scale, teamwork with very thorough statistical testing and evaluation, which now has become extremely reliable and reproducible. Preclinical research has had also its qualms, and many empirical evaluations have shown very low replication rates in preclinical research that is supposed to inform the development of new drugs. For example, in one such evaluation, only 6 of 53 landmark studies for Amgen oncology drug target projects could be replicated, and Glenn Begley concluded that the failure to win the war on cancer has been blamed on many factors, but recently a new culprit has emerged. Too many basic scientific discoveries are wrong. This leads to a lot of tension, or what I call the reproducibility wars. For fields that are not very familiar with the need to reproduce results, whenever you have a result that is not reproduced, people think that they're told that they're frauds and fraudulent, and that they need to retract the paper. And this is not so. I think that we need to understand that even with the best circumstances and with the best intentions, much of the research effort that we're putting together will lead to results that are not reproducible. And we just need to test that to find out which ones are reproducible and which ones should move forward and become the building blocks for the next round of research investigation. there's a lot of resistance to refutation. It's not nice to be told that my research has been refuted. People will fight back. We see that papers that are clearly refuted continue to be cited very heavily. Sometimes they refute the refutations. Very often they just ignore the refutations. Biases also operate differently in different scientific fields. A few years ago, along with Dan Fanelli and Rodrigo Costas, we got a very large number of meta-analyses, over 3,000 of them, with over 200,000 randomized, actually studies worth of data. And we asked, do we see footprints of different types of biases in these meta-analyses? If you have a meta-analysis, this means that people have thought that different studies are similar enough to put them together in the same forest plot. So you can ask, what if this bias is present? What would that meta-analysis look like? And if you have many meta-analyses across many topics, you can get an average impression of whether the patterns of the evidence are compatible with these different types of bias. And we could see footprint for practically almost all of these potential biases, but the magnitude of the footprint was different across scientific fields, meaning that some fields are facing a bigger problem with some types of bias compared to others, and it's not really that one size fits all. However, there are solutions that have been used, and some of them very successfully so, in specific fields to diminish these biases and make research more true and more valid. And I would argue that thinking about these solutions in fields that have not adopted them yet, on whether they might be a good idea for them, and maybe testing them out and see whether they could make a difference, might be useful. So these are some research practices that may help improve the situation: large-scale collaboration, adoption of replication culture, registration practices, sharing practices, reproducibility checks, containment of conflicted sponsors and authors, more appropriate statistical methods, standardizing definitions and analysis, more stringent thresholds for claiming discoveries or successes, improvement of study design standards, improvements in peer review, reporting and dissemination of research, and better training of the scientific workforce in methods and statistical literacy. Let's take a look at some of the ongoing initiatives to make these improvements more real. Sharing is something that has improved substantially over time. Several scientific fields have realized that without sharing, it's very difficult to really tell much. This is one paper that I co-authored with many colleagues in science a couple of years ago, where we argued that the default for genomic data is that they should be publicly available for unrestricted use. Of course, there are exceptions, but they should be exceptions rather than the norm. Here's two other fields, psychiatry and psychology. Along with Tom Hardwick, we decided to build a data arc for the most highly cited papers in these two fields to have their raw data available for everyone to use and examine and reuse and synthesize with other information. So we reached out to all the investigators of these extremely highly cited studies, and we said, we will curate the data for you, no cost. You don't need to do anything, just give us what you have and we'll curate them and make them available. Some investigators did send their data, and some were already sharing their data anyhow, but the majority did not. And the reasons were not really what we expected. We thought that maybe people will say no, because we're still using the data and we want to get some more papers before we give them to our competitors. Actually, that was not a very common reason. The most common reason was that the data were outside of researchers' control. Very often, especially for industry-sponsored research, investigators who are the first authors or corresponding authors have not seen their own data. They trust some analyses that have been furnished to them. They put their names on these analyses, but they haven't seen the data. Now, I think that this is really problematic. We've seen the disaster with hydroxychloroquine, with the paper that was retracted in Lancet after it was realized that the data that were supposedly collected in 671 sites around the world actually did not exist at all. Several journals are making more requirements as part of an effort from the International Committee of Medical Journal Editors to have data sharing statements. And this is a sine qua non for most of the medical journals that matter in people's mind at the moment. However, making a data sharing statement does not mean that these data are eventually shared. So this is looking at the top impact factor journals in the last couple of years after this statements requirement was implemented. And of course, most of them said that they have a statement, and more than half said that they intend to make individual patient data available, but some had deposited these data in a repository that you could not access for free. And if you asked how many of them actually had these data right now available without any boundaries and without any obstacles, and it was only 2 out of these several hundreds of studies that had really made the data directly available. Should we worry about that? Well, I think the nightmare is if most of the literature is not reliable, it's fake, it's problematic. And could that be the case? John Carlisle, who is an editor in anesthesia, had been asking for the individual level data of all the trials that were submitted to the journal over a number of years. And he realized that a very large proportion of these data sets were completely impossible to be true. And he called these trials zombie trials. So he published his findings in anesthesia at an issue around Halloween. And I wrote an editorial for that paper saying that hundreds of thousands of zombie randomized trials are circulating among us. My calculation was that probably there's 300,000 clinical trials that may fit John Carlisle's zombie randomized trial definition. Of course, we can do better. This is 2 journals, PLOS Medicine and BMJ, that have had a policy of really making the data available to investigators who ask for them upon request, a precondition for publication. So we did ask investigators who had published their data and their trials in BMJ and PLOS Medicine to give us the data, to reanalyze them. And about half of them, 46% of them, did send us the data. We reanalyzed them, and we saw that practically in all cases, we could get very similar results compared to what had been published. So in a transparent environment, and one might say, well, this is a select sample of the best journals and the best investigators and the most willing investigators, but under good circumstances, you can get trust practically close to 100%. This is looking at some random samples that we procured of the entire PubMed over a number of years for how many papers are sharing their data. And you can see here that it was close to 0% at the beginning of the century, and now it's close to 25%. And we expanded that exercise to text mine practically all the open access biomedical literature to try to see how often there's data sharing, there's code sharing, conflicts of interest disclosure, funding disclosures, protocol registration, claims of novelty, and claims of replication. So you can see the clear improvement in data sharing, far less improvement in code sharing over time, substantial improvement in the proportion of papers that disclosures of conflicts and of funding. It doesn't mean that they're complete, but at least something is being stated about it. A little bit of action for protocol registration, but not much. Steadily, very high rates of papers that claim to be novel, and a little bit more replication claims over time. This is looking at another view of the same data and how they have evolved over time. The average 8.9% of data sharing is not that great, but if you look at the evolution over time, I think that this is favorable. And this is mapping these indicators of transparency and openness and reproducibility across these maps of science that I showed you at the very beginning. As you see, we see a lot of color when it comes to open access. We have a sizable proportion of the literature where at least you can read the paper without subscription. But this doesn't mean that you can read the research. The paper is more like an advertisement that some research has been done. We see some activity on data sharing and color that pertains to particular fields. So some part of the universe are still very dark and others are seeing more color. Far less for code sharing, and it's highly focused in specific areas that have acclimatized to code sharing. Far more color for conflicts of interest and funding, And you see very scattered activity for protocol registration in some scientific fields. Very large variability across journals. There's some journals, but really the minority, where almost everything is shared, and almost always you will see disclosures, and most often you will see even registered protocols, but the vast majority of journals are still very far from adopting these practices. As research is becoming more complex, we have even more requirements for reproducibility to be able to tell whether we can trust. Computational methods in particular are becoming increasingly complex, and when you have increasingly complex methods, this means that transparency becomes even less prominent unless you enhance the standards. So it's very easy to describe a linear regression. You just put the coefficients and the constant, and that would be it pretty much. But if you have deep neural network algorithms, you really need to describe very carefully all the steps, all the sequences of decisions, and all the operations that were made to make the model run eventually. And recently we published that paper in Nature, where we dissect different possibilities about how to make artificial intelligence research more transparent and more reproducible. There's lots of resources, there's lots of possibilities. It's not that these research efforts need to be black boxes. They can be described in ways that would enhance trust among users of that research and would allow us to build confidently upon them for the next round of scientific investigation. As I said from the beginning, different scientific fields have different patterns of adopting these methods. We have run empirical studies in biomedicine, in psychology, in social sciences. As you see, they materially differ in terms of the use of open access principles, whether materials are readily available, whether data are available. Biomedicine is doing better, especially in the last few years compared to almost any other field, and analysis tend to be not very transparent. Pre-registration, very little activity across most fields. Protocol availability, again, very little, and scattered successes for confidence in regards to conflicts of interest and funding. How do we get to a situation where we can put more trust in research that it is reproducible and useful? I think we need to align our incentives in ways that would favor scientists producing reproducible and useful research. Until now, most of our reward systems are supporting productivity, and I have nothing against productivity, writing papers, publishing papers, making them visible. I have no way that I would attack that, but at the same time, we need to put emphasis on the other components of the PQRST electrocardiogram of appraising and rewarding research. So we need quality, we need reproducibility, we need sharing of data and resources, and we need translational impact to be part of our reward system, to be part of our incentives that funders, institutions, societies, other stakeholders are offering to investigators, to scientists, to align their work and their productivity to these other features. Last year, we published that paper in BMJ along with David Moher and his team, where we looked at what are the promotion criteria and the tenure criteria in faculties of biomedical science among universities worldwide. And we had data from 92 universities around the world. We realized that the majority of them use very traditional criteria, focused mostly on productivity, and very rarely would they use criteria that are better aligned with these new type of more reliable, more reproducible research. For example, mention of alternative metrics for sharing research happened in only 3 institutions. Data sharing was mentioned only once. And for many other criteria, they were not really mentioned in any of the official documents. This doesn't mean that promotion committees do not consider those. I think that these documents are just the guidance, and perhaps more scientists are sensitized to these issues and they are considering more seriously during their decisions on promotion and tenure. But I think it is important to try to move many of these features to the mainstream of how we appraise and reward research as you see here, at all levels of assistant, associate, full professor, and tenure, the traditional criteria are overwhelming compared to this new wave of criteria. To conclude, science, I think, is the best thing that has happened to humans, and we need to invest more in research, especially high quality, reproducible, and useful research. The reproducibility of many disciplines of scientific investigation has substantial room for improvement. There are many possible interventions that may improve the efficiency of research practices and the reproducibility and eventually the utility also of the evidence when it comes to applied research. Transparency, openness, and sharing are likely to help, but details on how to do this can be important. And the landscape of reproducibility is currently changing very rapidly, and we need to grasp that opportunity. We have an opportunity to make greater progress when a field is changing more fast compared to what it used to. I want to thank you for your patience and for the honor of inviting me to give this lecture. And I also want to offer special thanks to a number of my colleagues who have joined in some of the empirical work that I shared with you today. A million thanks.
Thank you so much, John. I suppose this is around, it goes in some ways back to the question you were saying right at the very end about motivation. How do you motivate people to behave differently? Because in some ways, you've analyzed the problem in a very comprehensive way. You've set out ways in which people should behave differently in order to overcome that problem. But how far do you think the community believes there's a problem and therefore wants to motivate themselves differently? Have you, since 2005, managed to persuade a large number of people that this is a problem that needs solving, or is that still a challenge itself?
I think that there's a large variability across different scientific fields and also different levels of resistance. But surveys have suggested that the large majority of scientists do believe that these are important issues. Nature, for example, has published a survey that showed that about 70% of scientists believe that these are important issues, that there is a problem, that we need to act on it. And of course, surveys can be biased because people who believe that there's a problem maybe are more likely to respond. But biases could be in either direction. It's not necessarily that this is an overestimate. In my experience, the greatest progress has happened in fields where leading investigators and also a grassroots movement among the average investigator in the field, they realize that this is not some sort of a police force that is trying to extraneously impose extra rules and extra bureaucracy and make our life more difficult. Life for a researcher is already so difficult to start with that we don't want more of that. They realize that this is part of the scientific method. This is integral to the scientific method. This is integral to the chances of our work being successful. It is integral to the chances that we get more by doing the same amount of work, that we get something that will be more likely to be a major discovery, more likely to be translatable to something that is effective, more likely to be a successful discipline. So, and this is exactly how people should see it. When scientists see that, then they do adopt methods that make their life easier and their work more efficient and their products more reliable and more visible in the wider scientific community. Not every single field has done that. So in that universe that I showed you, there's still lots of very dark areas that probably you don't want to go to, and others that are very sunny. And I do hope to see more color eventually.
I've got a question here, which is, do we lack formal training in peer review? Peer review is sort of so central to the method, but are we doing peer review professionally enough?
Peer review is a bit like democracy. It's a horrible political system, but it's the best that there is. And based on what we know, probably about 30% of the peer-reviewed papers get better compared to before their peer review. About 5% get worse because of peer review, and about 2/3 are not really materially touched. So peer review is not perfect, but it can help. And we are struggling to understand what is the best way to optimize peer review at different levels: pre-proposal, during the proposal, pre-publication, post-publication, different types of mix of that, internally, externally, by journals, by regulators, by other stakeholders, by the general public. We have seen actually a complete recast of the whole notion of peer review during the COVID pandemic. Many ways of publishing, especially in the biomedical sciences, like preprints that were not really widely used, became very widely used. So you had a lot of pre-publication peer review in the medical sciences, much in the same way as we used to have in physical sciences. Almost no one knows how to peer review a paper. I have been an editor and a member of the editorial board of many journals, and I have peer reviewed lots of papers. And every time I do this, I feel a little bit ashamed in a way that, goodness, I'm trying to get into this paper within a very short period of time. What institution did I train on for peer review? None. Is there such an institution? Is there such a setting that someone can train in peer review? We have all learned mostly by experience, by reading papers, by having our hands on, hopefully, in some similar type of work. But this is clearly suboptimal. There's not really official training, and it's not part of what is happening in the training of most scientists. Some investigators, some senior investigators, are allowing more peer review experiences for their junior investigators, and sometimes they also invest some time going over the papers that they're examining together. It's not easy, and I don't have a perfect answer on how we can do that, but I'm sure that there's plenty of room to improve both the training and the output of peer review.
Thank you. I've got another question here, which is, thank you for the great talk. Do you think there is value in encouraging sharing of negative results? And if so, how should the scientific community encourage that?
Negative results are at least as good, and often they're more important than positive results. If you think of information gain and the consequences of having some negative results published, much of the time, I would say most of the time, they have more information gain and more value compared to positive results. For example, if you have a definitive negative result, that can help you to avoid wasting effort and resources and money and time and everything down a path that is not going to be very high yield, or it's going to be no yield. And I think that in the current environment, where we're mostly seeking relatively subtle signals, which means that our initial chances of success just upon the first shot are pretty low, most of the results that are true are going to be negative. So discovery, a positive result, has very little value. I have even published a paper where I show that discovery has negative value. We tend to honor discovery, but a first discovery usually has negative value for science. Replication has lots of value, and a negative result typically has also substantial value. So if we have that mindset, then we should not really differentiate between negative and positive results. All of them need to be published. They're equally exciting, equally interesting, equally part of a continuum of evidence. And I think many fields have realized that, and these fields are more reliable overall compared to others. They're likely to make more progress. They're likely to lead to something that eventually changes our world, compared to others that just stick to a narrative of quote unquote positive results that are just science fiction.
I've got a few more questions I'd like to keep going with, if I may. One is a question about pre-registration. If your data reveals interesting patterns, is it invalid to analyze these if they were not in your pre-registration? Surely not always. So what do we do?
I love exploratory analysis. I have done zillions of them myself, and I have no remorses for them, but they are exploratory analysis. And I think that if they're specified as such, then I see absolutely no problem. There are some designs that probably you can pre-specify almost everything. Research is still full of surprises. There may be things that one has not anticipated that they need to be specified downstream. And also, as you say, there's lots of patterns that emerge that you have not thought and that are so stark that it would be a shame not to describe them and not do something about them. It's there's a huge continuum from entirely exploratory research all the way to entirely confirmatory research. I'm not going to say that one is better than the other. We need the whole spectrum. And what is important is to be able to be clear about what was exploratory and what was confirmation. So within a confirmation protocol that has been pre-registered, there may be superimposed exploratory research that may be very interesting. And it's worthwhile doing, but it just has to be specified that that's not something that I thought ahead of time. I just saw it and then I went down that path and look at this. Now someone needs to confirm it.
We have one from our governing body fellow, Matt Costa. Thank you. I've often thought that patients would be better off if 90% of the medical journals in existence were removed. Do you have a view?
Well, I'm not sure. I think that 90% of papers could easily go away without much loss. Probably 90% of my papers could go away with no loss of value. But at the same time, if we say that we restrict opportunities for publication and we have very few slots available for work to be published, then we superimpose a filtering process that it is unlikely to be met based on our ability to peer review, our ability to tell whether some research is high quality, transparent, let alone credible and useful. There's a lot of surprise in research. So at face value, when you first see a result, it's very difficult to say that this is true. It's very difficult to say that this will lead to something major. Innovation is in the eyes of the beholder. Who is going to judge that? So if you say that I will not give opportunities for people to publish, there's some variance to that. For example, some people say I will only allow you to publish up to a certain number of papers per year. And once you reach your maximum, you're done for the year. Wait for the next year then. I think this will make things worse. It will just make this publication and selective reporting bias more prominent. People will just cherry pick even more. They will select the most extreme and relatively probably less reproducible results to be published in these few slots. So I'm more in favor of allowing publication, but knowing that publication alone does not mean much. It's just a data point in a much larger universe. It may be easily refuted, it may be easily amended, it may be easily expanded.
I have somebody else going back to the question of peer review. I don't know exact numbers, but my sense is that the number of publications and the scientific information gain over time increases more rapidly than the number of researchers. And this means peer review becomes further detached from the radius of deep knowledge about any topic. I sense that more and more peer review therefore veers into more subjective reasoning. Would you agree with this trend?
There are a number of empirical studies on peer review. And as I said, most of them suggest that much peer review is not really very knowledgeable, is not really improving papers very much or at all. And also it is becoming more and more difficult to find knowledgeable peer reviewers who are willing to meaningfully review papers. Sometimes as an editor, I had to go after a couple of dozen invited peer reviewers, try to get one to respond, and then 3 months later, you get a single paragraph with a couple of typos to be corrected, and the paper has not really been touched. So it is true that we have a very large number of scientists. We have about 30 million scientists publishing papers. It's astonishing. And many of them venture into areas that they're not knowledgeable. Many review papers in fields that they're not knowledgeable. COVID-19 is a nice example. This feeling of hands on deck, which was indispensable because we were facing a major crisis, led within a few months 500,000 authors publishing papers on COVID-19. We had more than 200,000 papers published within a few months, and that included more than 500,000 different authors. Many of them came from fields that were completely remote. There's 174 fields in science that, according to science metric classification, and until a few months ago, I could say that no one from automobile engineering published on COVID-19, but recently even automobile engineering experts published on COVID-19. So it's, and I'm sure that automobile engineering experts have peer-reviewed papers on COVID-19 just as well.
John, can I ask a last question, because our time is coming to an end, and this sort of goes a little bit to the relationship between science and the media and science and politics, and any thoughts, reflections you have on, the last year you've had, the way you got caught up in the politics of COVID-19, but just any reflections you have on what that means for the general question of how science talks to the media and to politicians in ways that are productive rather than reductive.
This is a question that we can spend hours on. And I have to say that before the COVID-19 pandemic, my greatest remorse was that science was not reaching out to a large segment of the population, that most people were not interested in science, that science is the best thing that has happened to humans, but most people don't care about science. So suddenly with COVID-19, we have everybody being interested in science. And here you see that maybe you should not pray for something that you're not prepared, because at least myself, I was not prepared for this massive influx of communication demand and of trying to convey scientific evidence to people who were scared, who were in great fear, who were seeing tragedies all around them, who had very strong beliefs, who thought that they were under attack by a virus and by the measures, and they had strong ideologies and strong political beliefs and different types of agendas. Basically, politics is horrible when it interferes with science. I think science needs to be detached and retain its independence, not be smeared with politics. I think that communicating with the general public is essential. If you take a stance that is political, this is going to backfire. You may become a hero for some people, but you will become a demon for others. And unfortunately, this does become the case even if you avoid it by all means. I saw that even though I'm completely apolitical and I have struggled to say this is science, this is not politics, people will read every single sentence, every single paper as how does it fit to my ideology? What does it mean? Is this a friend? Is it an enemy? And they go into that thinking of we have a war, and a war not against the virus, unfortunately, but against our enemies who think differently. And we need to destroy our enemies with all possible ways and all arguments and all lack of arguments. So it's a huge mess. And I think that you can only resort to sticking to the scientific method, trying to say what you know, what you don't know, how much uncertainty we face, and try to be tolerant. Try to acknowledge that even people who attack you, the vast majority of them are not paid by some corporation to do this. They're just afraid, they're just in a very difficult set of circumstances. Try to show some empathy and try to show respect for everyone. I think that respect and tolerance and allowing for correcting science in an iterative fashion is probably the best recipe that we can hope for.
John, thank you very much indeed. And our hour is up of your time, so we're very, very grateful to you for joining us. I mean, that really was a wonderful tour, both in the hard data, but also the conclusions one can extract from it, There's a lot in there about human nature and how you motivate people to behave differently. We actually, next year's Haldane Lecture is being given by Chris Whitty, who's the government's chief medical officer here in Britain, a former alumnus of the college. And he's got to face all those issues we're just describing day by day. So it'd be interesting to hear how he deals with it. But John, thank you so much from everyone. Normally at this point, there would be loud echoing applause. We would be ushering you into a room where you could talk to the audience and then have a lovely Oxford dinner. I'm sorry we can't do that today, but when you're next in Oxford, it'll be lovely to see you here at Wolfson. But thank you so much for your time. It's been an inspiration.
A million thanks. It was a great honor for me. And I look forward to seeing you in Oxford sometime, hopefully soon.
Brilliant. And thank you very much, everyone, for joining us this evening. Thank you very much.